Okay, the next today, day 4 of the course, we're dealing with a totally new kind of problem. Now, as I mentioned in the early introduction, is that this week we are modeling mostly. We started with linear programming, then did networks, then did integer programming, and now we're talking about dynamic programming. The only difference with dynamic programming is that there is no set software to solve dynamic programming problems. We will be solving them by hand, which may be a little frustrating. We'll either be formulating them, something called the Bellman equation, which is you just have to set up the equation and define the variables. We will be also solving some by hand. Dynamic programming is more of a concept, an approach to solving problems. It relies on a very detailed structure, but it's different than what we've been talking about so far. It originated with Richard Bellman, but his name to some extent has been forgotten because the method seems so obvious and so self-apparent that it's kind of hard to think that actually somebody had to think of this. The truth is that it is kind of ingenious just because of its simplicity, and nobody did think of it until Richard Bellman came to the scene. So again, just its name, it's dynamic programming. Now, dynamic programming problems require that you set up the problem in a certain way, with a certain structure, from a certain point of view. And then the technique for solving it becomes self-apparent. The nice thing about dynamic programming is that there are no restrictions on linearity. It is a concept that is very, very broad in terms of the number of problems, the kinds of problems that can be solved with it. It is very commonly used in my experience within the electricity sector. We solved it. There's a complicated Niagara Falls problem, which I may mention. We also use it for something called unit commitment problem, which is the problem of deciding when units should be started and when units should be shut down. Obviously, there's less demand at night and over the weekends, so students are brought up to, units are brought up, what is called, are started to meet the demand hours, and then at a certain point you don't need as many units on the system, so they're shut down. And what is the optimum time at which units should be committed? That problem is now, for a while there, integer programming and dynamic programming were competing with each other for solving that problem, and dynamic programming won out, and that's the standard approach. So the best way of explaining dynamic programming, I find, is through a classical example. And the example requires, it involves a salesman that is traveling. And the only reason that I will use the United States is because in Canada, there really is only one east-west highway, and there really isn't much latitude. So I'm going to say that imagine that a salesperson starts over here maybe in PEI, okay, and has to go all the way down to California, LA. And let's say that there's cities that he can visit. And the question is, which cities should he visit that will maximize his overall profit for the trip? Now, what dynamic programming requires is stages. It has certain keywords which have to be defined for every problem. So you ask yourself, what are the stages in this particular problem, or in any problem that you're faced? The format of this part of the course will be exactly the same as in the previous days. I will talk generally about the method, and then we'll do 3 problems from the problem set, and then leave it for you guys to try the rest, and guys and gals, try the rest, and then we'll come back again, and you let me know by 3 o'clock which ones you want me to take up. But let's deal with this particular person. He starts in PEI and he ends up in LA, and you require stages. One of the key elements of every DP is stages. Without stages, you don't have a dynamic program model. So you need to be able to define what are the stages. Well, what we will do is we will define the stages as sort of lines like this. And we will make an assumption that the salesperson will not visit the same city on each of these lines. So he buys the tickets that always requires him to fly west. And the question is, let's say there's another city here. The question is, what is the optimal way to travel from PEI? Which city should he go to first? And after that, which of these should he go first? And so on and so forth. And then to get to LA. Well, all these problems are solved. All these problems are solved backwards. We assume that he has arrived at the stage. He will have arrived in LA at some point. And then looking back, he could have been in any of the cities at the last stage. So each of these is a stage. Okay, so we've already determined that these are the stages. So now we're at the last stage, and we don't know which is the optimal city to have gone through. But we do know one thing, that once he lands up at each of these stages, there is only one way to go, and that is to fly to LA. That is the optimal thing to do. It's not the optimal thing, it's the only thing that he can do once he's there. Now, the key in dynamic programming is that no matter what city you go through, you have to indicate what should he do next. Well, in this last stage, it is very obvious that the thing to do is to go to LA. But we can record what the benefit is of having been in each of these cities. So there will be a number, 342, I'm making up some numbers, 376, and 285. So it would seem to be that 285 is the worst profit, but it's possible that perhaps, given the money that it takes to fly from one city to another, maybe that is the optimal route. It doesn't mean that it isn't the optimal route. So what we do then is we go one stage back and we go to each of these cities and we say, okay, imagine that the optimal route takes us to this city. What is the best thing to do? Well, you know that if you go this way, then the profit is 342. The question is, how much does it cost to travel there, and what is the profit that you make in this current city? So it's the profit in the current city minus the cost of getting to the city plus the net profit after that. And the net profit after that is the profit you make here minus whatever the cost to go to an LA. And let's assume that once he gets to LA, he just goes to the beach. So we can write down 416, make up these numbers, 512, and 422. And so what you do now, the 416, the best thing to do, let's say, is to go this way if you end up there. And maybe if you go through here, the best thing to do is to go up to 342. And if the best thing here is to go to 285, let's say. So you put up signs as you do this analysis. And you keep on doing this analysis on and on and on and on. And until you finally get to PEI. And when you get to PEI, you then do the analysis to find out what the optimal objective is. And it may turn out to be that $3,212 is the highest profit route, and the way you start that route is by going to this city here. Now, the strange thing with dynamic programming is that you get to find out what the value of the objective is before you know how to accomplish it. So you first find out that the optimal profit of this strip is 3212, and then you know what the optimal way to start, and then you backtrack to each of these. One may have calculated 2612, 2813, and 2542. I'm just making up these numbers, and this one tells you go that route there, because that is the one that is going to be the optimal, even though this may look better right now. So, and then this will have signs. So once you know what the optimal is, then you have to backtrack and follow the signs, and that's how you find out how the rest of the route is. So the key is that you need stages, and that is the main part right now. And I've just given you some indication of how you solve these problems. It's a little abstract at this point, but let's continue in the next video.